late 2015, SpaceX revolutionized the space industry by recovering their first stage of their rockets instead of letting them fall to the Earth uncontrolled. The second stage, on the other hand, is never recovered. But why? Let's review a flight profile of a Falcon 9's first and second stage to understand why the first stage is recovered while the second stage is not. We will specifically look into the differences between their engines and the maximum velocity of each stage, as these are the key reasons why only the first stage is recovered. A Falcon 9 fully fueled weighs more than two 787 passenger jets at 500,000 kilograms or 1.1 million pounds. The 9 Merlin engines on the first stage at full thrust provide 7,560 kilonewtons or 1.7 million pounds of thrust. This equates to roughly 12 Boeing 787 jets at takeoff. Vertical on the launch pad, once the countdown reaches T0, the Falcon 9 ignites its engines and the rocket begins its ascent to outer space. Within seconds, the rocket has cleared the tower and begins accelerating at a blistering rate, fighting the dense atmosphere. Just over 1 minute into flight, the rocket is already at cruising altitude of passenger jets and going 20% faster. Now that the atmosphere is only 15% as dense as it is at sea level, a very unique physical phenomena is evident. This is the widening of the exhaust plume. Let's briefly look into the design of a rocket engine and the plume it produces, as it's important in answering our question of why only the first stage is recovered. First, the basics. This is a Merlin 1D engine. The Falcon 9 has 9 of them on the first stage. The engine produces thrust by burning fuel and projecting it in the opposite direction of where the rocket wants to go. A simplified version of this thrust formula is found through multiplying the amount of fuel that is being projected through the engine by the velocity in which the fuel was projected with. You can see here how the faster the fuel is thrown out of the rocket, the greater the force will be, using the same amount of fuel. This projection of the fuel creates a force, and according to Newton's third law, this force projected down will push the rocket up with the same force. So the goal of the engine is to get these exhaust particles going as fast as possible. The factor that determines the velocity of these exhaust gases is the size of the nozzle. Let's look at how the size of the nozzle is able to control the exhaust velocity. Following the path of the exhaust gases, they start in the combustion chamber, where oxygen and fuel are mixed together. They then leave the combustion chamber at a very high pressure, temperature, and velocity. This is where things get interesting. The nozzle converts pressure and thermal energy into velocity. The wider the nozzle is, the faster the exhaust particles will be, and the lower pressure and temperature the exhaust will also be. Merlin engines, like the ones on the first stage of the Falcon 9, have a nozzle diameter of 0.9 meters. This results in an exhaust exiting the nozzle at over 9,000 kilometers an hour and at a pressure of 0.7 atmospheres. The relationship between the exhaust pressure and atmospheric pressure around the rocket play an important role in the rocket's efficiency. At liftoff, the ambient air pressure is 1 atmosphere, and of course the exhaust pressure is at a constant 0.7 atmospheres. A nozzle in this relationship is referred to as an overexpanded nozzle because the ambient air pressure is greater than the exhaust pressure. There are certain inefficiencies linked with an overexpanded nozzle. The higher ambient pressure around the rocket's exhaust will squeeze the exhaust and force the exhaust towards the center line of each nozzle. The result of this is the exhaust is no longer being projected straight down away from the rocket. This in return lowers the efficiency of each engine because remember, the exhaust projected straight down will push the rocket straight up with the same force. A sign of an overexpanded nozzle is the Mach diamonds that are produced in the rocket's exhaust. This is where the exhaust pressure gets compressed and then expands over and over again as it interacts with the relatively high ambient air pressure. But the rocket doesn't stay overexpanded for long. As the rocket climbs in altitude into lower air pressure, eventually the ambient air pressure will be equal to the exhaust pressure. This happens at roughly 40 seconds into flight. When the rocket is 3.5 kilometers in altitude, the rocket now has an ambient nozzle, and this is where the engine is most efficient. Because remember, the closer the exhaust pressure is to the ambient air pressure, the more efficient the rocket will be. An ambient nozzle looks like this. a perfect column of flame, as both pressures are equal. As the rocket continues to climb in altitude and the ambient air pressure continues to lower, the exhaust pressure will now be greater than the ambient air pressure. This engine now has an under-expanded nozzle. The low ambient air pressure allows the exhaust pressure to expand into a wider plume. This is also a sign of inefficiency, as the rocket is beginning to project fuel horizontal to its heading. Now, because the rocket spends such a small portion of its flight in low altitudes and a large portion of its flight in high altitudes, a question develops. Why not design the engine to be more efficient later into its flight in high altitudes by expanding the nozzle size and converting more thermal energy and pressure into exhaust velocity? Well, there's two reasons why we can't design our engine to operate in lower atmospheric pressure. The first reason is reduced efficiency at liftoff. Remember, the further the exhaust pressure is from the atmospheric pressure, the less efficient the rocket will be. If our engine runs at 0.2 atmospheres, for example, there will be a greater difference in pressures at sea level, and the engine will be more overexpanded. But there's even a bigger reason why we can't design the engine for higher altitude flight. The engine at low altitudes will be damaged through something called flow separation. Flow separation is when the relatively high ambient air pressure, the blue arrows, will push itself in between the nozzle walls and low pressure exhaust. These fluctuating pressures will cause pressure spikes within the nozzle and damage it. This happens when the rocket exhaust is less than roughly 40% of the ambient air around it. Because the first stage must run at sea level, where the ambient air pressure is 1 atmosphere, this constricts the exhaust nozzle for the first stage engines to 0.9 meters in diameter. As the Falcon 9 continues to increase its altitude, you can see it begin to change its trajectory. Instead of going straight up, it's starting to travel horizontal to the Earth's surface, but why? The reason for this is to achieve orbit. Let's quickly review the principles of orbit to understand why the Falcon 9 is lowering its heading. If the Falcon 9 was to only head vertically away from Earth, once it runs out of fuel, gravity would slow it down to a stop and then pull it back to Earth to roughly exactly where it took off. Just like throwing a tennis ball in the air. But when the Falcon 9 begins to lower its heading, the faster the Falcon 9 goes, the further from the launch pad it will land. If the Falcon 9 continues to gain horizontal velocity, something very unique happens. The Falcon 9 would never fall back to Earth. It's traveling away from Earth just as fast as gravity is pulling it back to Earth. This is achieving orbital velocity. But here's our problem. We understand that we need to be going a lot faster to achieve orbital velocity, but as the air thins, our engines get more underexpanded as its efficiency decreases. The first stage is also running out of fuel. This is where the second stage becomes functional. At just over 2.5 minutes of flight, the first stage cuts off its engines. This is referred to as MECO, main engine cutoff. The first and second stage separate, and the second stage starts its Merlin vacuum engine and begins to accelerate the payload once again. How does the vacuum engine differ from the first stage engine? Well, the vacuum engine is very similar to the first stage engine except for one critical component. This is, of course, the nozzle size. Remember how an optimally designed engine has an exhaust pressure that equals the ambient air pressure. Well, operating in the near-perfect vacuum of space, this means the nozzle cannot be large enough. Therefore, the size of the nozzle on the second stage is limited by weight and size at a massive 3.3 meter wide nozzle. As the second stage continues to accelerate to achieve orbital velocity, the first stage will begin to orient itself into a controlled fall back to Earth, using its nitrogen thrusters, grid fins, and later its engines to slow its descent. Once the second stage has achieved orbit, it will cut off its engine. This is known as SECO, second engine cutoff. Around this time, the Falcon's first stage is approaching the ground. It uses one engine to slow its descent to a stop and gently land on an autonomous drone ship that is strategically placed several hundred kilometers out to sea. In landing on the drone ship instead of flying back to the launch pad, the rocket doesn't have to reserve fuel to fly home. This allows a greater amount of fuel spent accelerating the second stage. While the first stage heads back to land, the second stage is traveling at a blistering 27,000 kilometers an hour at an altitude of 200 kilometers. The second stage then deploys its payload in this orbit and is therefore no longer needed. So why does SpaceX recover the first stage but not the second? Well, looking back at the differences between the two stages at their times of separation, the second stage separates at orbital velocity, which is 4 times faster than the speed of the first stage at its separation. If the second stage entered the Earth's atmosphere at this speed, it would burn up through friction from the air it would push through. Refiring its vacuum engine to lower its velocity would only work until the engine is in the atmosphere, where it would be grossly overexpanded and would be damaged through flow separation. Additionally, any weight that is brought onto the second stage through efforts to recover it, like heat shields, parachutes, or fuel reserves, would force a subtraction of weight from the payload's capacity. So instead, SpaceX has decided to only recover the first stage of their Falcon 9 rocket, which is substantial enough to make space much more accessible. Thanks for watching this animation, and I'll see you on the next one.